Hi, everyone, and welcome to Lesson 2.2, Part 2. It's a lot of twos. In this lesson, we're going to dive much deeper into the normal distribution and discuss what Table A is and how to use different means of technology for computing some normal distributions. So we're going to start with a approximately normal distribution. That's a really big word there, approximately normal. And we're going to base this context off of the movie Back to the Future. If you haven't watched it, I recommend you doing so. With that said, we are going to start with this approximately normal distribution. Reading the context, after accelerating for 20 seconds, DeLorean, you're not always going to reach exactly the same speed. So after accelerating for 20 seconds, the distribution of speed is approximately normal with the mean of 80 and a standard deviation of 7.7. So let's go ahead and label our normal distribution here. So one standard deviation above the mean, 87.7, 95.4, and 103.1. That gives our three standard deviations above, 72.3, 64.6, and 56.9. Now, use these values to answer items 2, 3, 4, and 5. Base your percentages on, of course, our standard normal distribution and the 68, 95, 97 rule. So why don't you go ahead and I will fill them in and we'll debrief after. So I've got a couple of answers for 2, 3, and 4. The way I explain it might be a little bit different than the way you calculated it, but we should all be coming up with the same values. Using our standard normal distribution, our 68, 95, 97 rule, you break it into different chunks that fall within certain standard deviations, of course. So if we want greater than 87.7, what we're looking for is this region right here. So how did I go about doing that? I personally said 100 minus 68. Why did I do that? Well, 68, remember, is right here. So what I was thinking was that if 68 is the red region, then 32 is then the blue region, and greater than 87 is one half of that blue region. That's how I got 16%. The alternative would have been to add up 13.5, 2.35, and 0.15 to get 16%. Either way, either one of those things would work. So that was number 2. Number 3, what percentage were between? So let's go ahead and shade that. So between 64 and 87. So now we've got this. So once again, we've got that 68 within one standard deviation. And then using this number from the standard normal 13.5, that's where I got my 13.5 and my 68. To get 81.5%. And then finally, what percentage will be less than 64.6? Once again, the idea is 64.6 is that 2 standard deviations below. Remember, within 2 standard deviations, we are at 95%. So this whole thing would be 95%. And below 64.6 would be half of the leftovers, so that's where 5 divided by 2 equals 2.5% left. Again, same thing over here, 2.35 plus 0.15 also gives you 2.5%. So as usual, there's a couple of ways to go about any of these problems. So where does that leave us with number 5? If you thought through for a quick second, I accidentally erased my 64.6 here. Now, if we're in number 5, what is the problem? 68.45 falls somewhere in this region. somewhere between 1 standard deviation below the mean and 2 standard deviations below the mean. So exactly how many standard deviations below the mean is 68.45? Well, that's where we have to compute a z-score. So why don't you pause the video and compute the z-score for 68.45, and then we're going to go from there. Hopefully you got that z is equal to negative 1.5. So let's remember what that means. Contextually, a speed of 68.45 miles per hour is 1.5 standard deviations below the mean. Remember, complete sentences and context are everything. So what's the problem here? The big problem is that for 2, 3, and 4, we were able to successfully use the 68, 95, 99.7 empirical rule for our percentage, for our probability of this happening. But that was because these numbers were tailored very nicely, and all of the numbers in 2, 3, and 4 represented a whole number of standard deviations above or below the mean. So this one right here, 68.45, doesn't do that. So what's the problem? The 68, 95, 99.7 rule fails. What we need is something called Table A. And Table A is going to be a big reference sheet we come back to over and over and over this year. So let's take a look at it for the first time. So this is Table A. Like I said, this is going to be a reference sheet that we come back to over and over and over again. And what this is a list of z-values. Here on your left-hand side are z-values. And so that is z-values up to 1/10. And then what the columns represent is z is rounded to hundredths. So just picking 2 random points here. This one right here would be z equals negative 2.42. Whereas this one represents z equals negative 2.47. That's where you get from here and here. Okay, so what does that mean? What do these two numbers, 0.0078 and 0.0068, mean then, if that's the case? Well, what this means is the numbers inside the table here, these 4-digit decimals, represent the probability, represent the area to the left of a given z-value. So let's think about this for a second. Going back to standard normal, what is the area to the left of negative 1? It's 13.5 plus 2.35 plus this. In other words, it is 16, right? 16% is to the left of 1 standard deviation below the mean. Let's make sure that that's the case. Negative 1.0 standard deviations, this number looks an awful lot like 16%. All right, so there is a great deal of rounding in the Table A and the 68, 99, 68, 95, 99.7 rule. There is a lot of rounding, but we do have a little bit of flexibility in a lot of our numbers in stats class. So that's a brief overview of how to read Table A. Now let's use Table A to try to see it on your own. Try to use Table A to find the area to the left of negative 1.5. So first thing we need to do in order to find the area to the left of z equals negative 1.5 is find negative 1.5 on Table A. And here it is. Negative 1.50 would be that one right there. So this number, 0.0668, if this is z equals negative 1.5, 0.0668 is the area of this region right here. And so what that means is the percentage of the runs that the DeLorean will be less than 68.14 is 68.45 rather is 0.0668, which means 6.68% of runs will be less than 48.5. And so what we want to do is do a couple of these. I'm going to do number 6 with you. I'm going to help you through number 6, and then I'm going to ask you to see if you can figure out numbers 7 and 8. Okay, so how do we determine what percentage of runs will be greater than 85 miles per hour? What we need to do is we're still operating on the same mean and standard deviation. So what we want to do is draw a normal curve. We want to label the mean. We want to put the 85 here, and we want this right here. And so remember, we're looking at the table A here. And the table A isn't based on this 80, 85. In fact, what you want to do is, in addition to sketching it, you want to make sure that you are labeling that this is a normal distribution with 80 and 7.7. You want to use that correct notation so that when you draw the 80 and the 7.7, it is different from your standard normal 0, 1. Okay? But what is the same is you're going to need to compute the z value for 85. Okay? So let's start there. You want to compute the z value for 85, so that's going to be 85 minus 80 over 7.7, and that is 0.65. And now we'll go ahead and find 0.65 on table A. So what you notice is the left-hand data is the negatives, the right-hand data is the positives. So here's 0.65. And so go ahead and pull this number right here, 0.7422. But remember, 0.7422 is the area to the left. Area to left of z equals 0.65. So what do you want to do? From table A, you want to do the area equals 1 minus 0.7422, which is equal to 2578. So 25.78% of runs have a speed greater than 85 miles per hour. 25.78% of runs will reach 85 miles per hour or greater. Now, let's look at a couple of other ways that you can calculate this 25.78%. First things first, as usual, we can do this on Desmos. So let's learn how to do this on Desmos. So you'll have to do is in functions, and surprisingly, not in stats, but in distributions. And what you'll want to hit is normal distribution. And notice it is mean of 0 and standard deviation of 1. So what you'll want to do is check this here, CDF, cumulative probability, cumulative density function. And since we're dealing with mean of 0 and standard deviation, we're dealing with the standard normal. So the minimum value is 0.65, our z-score, and our maximum is infinity. If you hit this magnifying glass, this plus, it's actually going to shade it for you. And now notice this number, 0.2578, is pretty familiar. So that's a nice, easy way to do it. You can also do normal distribution, but instead of doing 0 and 1, we can do 88, comma, not 88, I'm sorry, I was in movie mode, 80, comma, 7.7, and we can choose 85 for our minimum and infinity for our max. Now if we hit this magnifying glass, it's going to zoom in and give us our sketch here based on this. And now we see why it's important to notate which normal curve we're talking about at all times. I will also, in just a moment, add a video for how to do this on a TI-84. So give me a quick moment to do that. And then afterwards, why don't you go ahead and try numbers 7 and 8 and see how it goes.
Okay, so now that we've looked at how to compute this 25.78% via table A and via Desmos, let's talk a little bit about how to do it on a TI-84. So what you want to do is we have been living in the stat menu so far. This one actually lives in the blue distribution menu. So you want to hit second and go to distribution. This one we will want to do with this command number 2 where it says normal CDF. And so that's normal cumulative density function. And so we'll want to set our lower bound, in this particular case, as 85. Our upper bound, remember this is asymptotic, so we want a nice big number, usually 99 suffices. You'll set your mean as 80 and your standard deviation as 7.7. And you'll hit paste. That'll paste it into the command line here. If you're using a TI-83, you'll actually have to manually enter these numbers. Lower, upper, mean, standard deviation separated by commas. You'll hit enter and that same 25 number will be spit out. There's going to be a little bit of rounding error and that kind of thing. So you will have some slight variations. If you want to be super fancy about it, you can go to this draw menu on the distribution, hit shade normal. You'll get, not 82, 85 for your lower, 99 for your upper, 80 for your mean, and 7.7 for your standard deviation. And when you hit draw, you'll get this picture here with that same computation. Now, you do have to fool around with the window quite a bit to see this real nicely. So it might not be hugely worth your time, but you might want to play around with that as you go. So hopefully this was helpful, and let me know.
Okay, so now that you've seen some calculator input, TI-84 input area, and had a chance to work through numbers 7 and 8, let's debrief on that a little bit. So what percentage will be between 70 and 95? So here's your lower and your upper, your notation, your z-scores for 70 and for 95, because we're going to pull values off of table A. So once you find your z-scores, what's going to happen is what you want to do is this 97.9744, remember, is the area to the left of 1.95, and this 0.0968 is the area to the left of negative 1.3. So what you're really going to want to do is take this value and chop it off, right? If you want to find the area between 1.3 and 1.95, you're going to want to take the blue region and subtract it from the red region. Okay, so that's why to calculate the area between these two guys, you're actually going to want to take this and subtract from it that to get 87.676% of the time. If you are doing it on Desmos, you'd want to either put it in directly with this normal distribution with 87.7 as is in red here, or you can keep it as the standard normal and put it in with z-scores. Notice you'll get the you'll get pretty much the same. You'll have a slight variation because the 1.3 and the 1.95 are rounded values. The next line is for the next problem, so we'll come back to that in just a second. And then, of course, if you want to do it on your TI-84, as explained in the previous video, you'd use the normal CDF function with your lower bound, your upper bound, your mean, and your standard deviation to get that same number. Right now, number 8 asks a slightly different question. It asks, what is the speed needed to be in the top 15% of all possible speeds? So we actually need to hunt out a speed to get a certain area. So the only way we're going to do that is through, well, not the only way. We're going to start is through our table A. I already have the answer written down. We'll talk about how I got that in just a second. So what we want to do is we want to find a region over here with 15%. Table A, remember, tells us this region, so we want to find the z value that has an area of 0.85. So let's find it. Zoom in a little bit. We want to find the number that gets closest to 0.85. That's going to be this number right here is going to be our closest to 1.85 to 0.85. And the z-score there is 1.04. Has the area over here at 0.85. That's why that's 15% to the right. So that's how I got 1.04. And so now let's put it back in context. Remember that z is equal to the value minus the mean over the standard deviation. We know that z is 1.04. We want to actually find the x value that has that z-score. So a little bit of algebra is in store here. And what we get is 88.2 miles per hour. So if anybody is familiar with the movie, according to this distribution, 15% of the time, a speed of 88.2 miles per hour will be achieved, or more. 88.2 miles per hour or more. So what's a technological way to calculate this? Well, on Desmos, what you'd have to do is you do normal distribution, type in your mean and your standard deviation, put a period. Then in functions, in the distribution functions, you'll find this inverse CDF function right there. I didn't want to do that again, though, so sorry about that. And so you'll do inverse CDF, and you'll put the area to the left that you want, and it'll calculate the percentage of runs that have that, the z value, the x value that gets you that percentage. So that's how you do it on Desmos. And then, of course, on your TI, I'll give video in just a second here, but you would find the inverse norm. You'd enter the percentage to the left, your mean, your standard deviation, and that's where you'd get your 88.2. One more thing before we totally debrief on this topic. It's really important to note what gets you full credit, because again, we are talking about AP tests. So for this style of problem, to get full credit, for not just number 8, but in general, what you're going to want to do is you're going to want the unstandardized picture. And the standardized picture. So in other words, here's your unstandardized and here's your standardized. And you need them both labeled with proper notation, as well as your mean and whatever critical values you're talking about. You're going to need your z-scores and formula, the z-score formulas, your work, and you're going to need your final answer. Now, work is going to be your any one of these things. This is called your work. Depending upon your technique, your work can be table A, your work can be Desmos, or your work can be TI-84, but you do need to be sure to write down which command it is that you're doing and which method, because you are going to get slightly different numbers, of course. All right, so now let's go ahead and, you know what, I'll write that down over here. So I didn't put my work for the Desmos version. So if you're going to do Desmos for the inverse norm, or the inverse norm, you're going to do normal dist 80, 7.7, period, inverse CDF of 0.85. And that's going to be your work for Desmos. All right, so now let's go ahead and move on to the important ideas topic and debrief on that, and do the check your understanding, and we'll be.
So now let's talk about how to do the inverse norm function on the TI-84. You'll actually see the commands down here. You'll see the syntax written right there. But what you'll want to do is, once again, enter the distribution. This particular case, you'll want to choose. Oops, sorry about that. You'll want to choose number 3, inverse norm. Again, your area. You'll want 0.85. If we're going to do left-hand area, you'll want your mean as 80. You'll want your standard deviation as 7.7. And again, you'll want left area to be 0.85. If you're using an 84 or some of the older, if you're using an 83 or some of the older 84s, this tail side might not be an option. That's why I'm doing it left first. It defaults to left to get your 87.89. Again, a little bit of round off error is inherent in all of these problems. And so that matches pretty closely to the answer we got via table A and via Desmos. So if you have an 84 though and want to do the right-hand tail, you'll enter the same set of commands, the same values, except you'll choose a right tail test. And you'll do, what did I do wrong here? I'm sorry, I forgot to change the 0.85. Mr. Dodd, that was very, very silly of me. Sorry about that. You'll want to change this. If you're going to do a right tail test, it's not the same syntax. You'll want to do 0.15 and 87.9 rounds to 88. 88 miles per hour is the speed at which time travel is possible. So hopefully you are following along okay and don't fall into the trap I made into this one.
So just to reiterate some of the really important parts here, your z-score, of course, is always value minus mean over standard deviation. You're going to become intimately familiar with that. You can find the area under normal curves using table A, using Desmos, or using TI-84s. If you're using TI-84s, normal CDF, your left, your minimum, your right boundary, your mean, and your standard deviation. That is the syntax for using the TI-84. Or, of course, you could be using the inverse normal to get the area to left. And then your mean and your standard deviation. As with any device, you do need to use proper syntax to get the right numbers. And then, of course, some reminders, draw pictures and label all the time and show your work. and you're showing your work is going to be that. Now, just to revisit the idea of drawing pictures and labels, I do want to bring you all the way back to the beginning. And we actually failed intentionally to do something so that I could revisit it. This one is not labeled properly. Yes, we labeled all of the mean and the multiples of the standard deviations, but it is vital to use proper notation on this here segment. So you do want to make sure that you're labeling 80 and 7.7. Even if you have everything labeled down here, it is critical to label this. Every normal curve gets a key, just like everything else we've talked about this year. Okay, so go ahead and try your hand at some of the check your understanding problems, and let me know how you do. And just to quickly finish things up, I have the two check your understanding problems all computed here. I used table A for each of these. This first one, hunting out z equals negative 1.75. And on the second one, finding the z value that represents 10% to the right, meaning 90% would be here on the left. So if you've got any questions, shoot me a message or ask me during class. Have a great